Hi, today we are going to look at derivatives of trigonometric functions. So we'll start out by looking at the six main trig functions, so our three primary as well as our reciprocal functions. So like I mentioned, we have our three derivatives of our primary trig functions as well as our derivatives of our reciprocal functions. So our derivative of sine x is cos x. Our derivative of cos x is negative sine x. Our derivative of tan x is secant squared x. Our derivative of cotangent x is negative cosecant squared x. Our derivative of secant x is secant x tan x. And our derivative of cosecant x is negative cosecant x cotangent x. Now, with all these derivatives, if we also have stuff within our trig functions, we also have to remember to utilize our chain rule. Okay, so first example, we want to differentiate y equals sine of 3x. So first I will differentiate this trig function, so that would give us y prime is equal to our derivative of sine x is cos x, but because we have sine of 3x, that's going to give us cos of 3x. And then because we had something other than x in here, we have to use chain rule. So we'll take the derivative of what was inside. So our derivative of 3x is 3, so we'll move that to front. So y prime is equal to 3 cos of 3x. Next example, we've got y equals sine of x plus 2. So our derivative of sine x is cos x. Now, because we have x plus 2, it'd be cos of x plus 2. So we've got y prime equals cos of x plus 2. And that, well, because we had something other than just x in here, we have to take the derivative of it using our chain rule. So d dx of x plus 2. Now our derivative of this is 1. 1 times this is just cos x plus 2. Okay, so next example, we have y equals sine of the square root of x squared plus 1. So as we've already dealt with in the first few examples, our derivative of sine is cos. So we know we've got y prime is equal to cos of the square root of x squared plus 1. But that's going to be because of our derivative multiplied by or chain rule multiplied by the derivative of x squared, or sorry, the square root of x squared plus 1. And then times the derivative of what's inside this root, so of x squared plus 1. That gives us y prime is equal to cos of the square root of x squared plus 1 times our derivative of x squared, or sorry, the square root of x squared plus 1, which would be 1 over 2 times the square root of x squared plus 1 times our derivative of x squared plus 1, which is 2x. Now, one thing you may notice right away, this will cancel with this. So when we combine this all together, that gives us y prime is equal to x cos of the square root of x squared plus 1 over the square root of x squared plus 1. Okay, next example, we've got y equals sine of x cubed. So that'd be y prime is equal to our derivative of sine, so cos of x cubed times the derivative of x cubed. Now our derivative of x cubed is 3x squared. So we can move that to the front, so that gives us 3x squared cos of x cubed. Our next example, we've got y equals sine cubed of x. Now, in this case, we take our derivative of the exponent first before doing the derivative of our trig function. So this would be y prime is equal to 3 sine squared x times our derivative of sine x. So that would be 3 sine squared x times cos x. Next example, we've got sine cubed of x squared minus 1. So once again, our derivative, we have to do the exponent on our sine first. So we'd have 3 sine squared of x squared minus 1 times our derivative of sine of x squared minus 1 times our derivative of x squared minus 1. So that gives us 3 sine squared of x squared minus 1 times our derivative of sine of x squared minus 1, so times cos of x squared minus 1 times our derivative of x squared minus 1, which is 2x. So we'll just reorder this slightly. So we've got y prime is equal to 6x sine squared x squared minus 1 times cos of x squared minus 1. Okay, so we'll do some more examples. Now we'll add in a few more rules, which will make things a bit more complex. So we must use our product rule to solve for this because we've got our x squared times our cos x. So if you recall, our product rule is we take the derivative of the first function, that's d dx of x squared, and then multiply it by our second function, and then add our first function times the derivative of our second function. So derivative of 2x, or sorry, x squared is 2x. and then times cos x plus x squared times our derivative of cos x, which is negative sine x. So we'll just multiply this out. So we've got 2x cos x minus x squared sine x. This next one, we have division. So we've got y equals sine x over cos 2x. That means we have to use our quotient rule. So if recall, that's taking the derivative of our first function, or our numerator. So d dx of sine x times our denominator minus our numerator times the derivative of our denominator all over our denominator squared. So that gives us our derivative of sine x is cos x. So we've got cos x times cos of 2x minus sine x times the derivative of cos 2x. So that would be negative sine of 2x. And then we have to deal with the chain rule. So times the derivative of 2x all over cos squared of 2x. So we've got y prime is equal to cos x times cos of 2x. These negatives will cancel out. So that's plus sine x. Actually, before we do that, we know the negatives will cancel out. When we take the derivative of 2x, we're just going to get 2. So we can move that to the front. So plus 2 sine x cos of 2x or sorry, sine of 2x over cos squared of 2x. Now we can also deal with implicit differentiation as well. So for example, given tan of x times y minus x equals cotangent y, we want to find dy dx. So we'll start by taking the derivative of both sides. So we have d dx of tan of xy minus x equals d dx of cotangent y. So we'll split this up. So this is d dx of tan x y minus d dx of x equals d dx of cotangent y. So our derivative of tan is secant squared. So therefore, our derivative of tan xy is secant squared xy. And then we've got stuff inside, so we've got times the derivative of xy minus our derivative of x, which is just going to be 1, equals our derivative of cotangent y is negative cosecant squared y. And then times our derivative of y, or d dx of y. So when we take the derivative of x times y, we have to, because these are multiplying, use our product rule. So we have secant squared of x times y times our derivative of x times y plus x times d dx of y minus 1 equals negative cosecant squared y times d dx of y, which is dy dx. So we have secant squared of x times y times the derivative of x, which is 1, times y is y, plus x times the derivative of y, which is dy dx, minus 1 equals negative cosecant squared y times dy dx. At this point, we'll want to multiply this out. So we have y times secant squared of xy plus x times secant squared of xy dy dx minus 1 equals negative cosecant squared y of dy times dy dx. At this point, I would move the terms of dy dx to one side, so I'd probably move this to this side because it's the least amount of things to move around. So that gives us y times secant squared xy minus 1 equals negative cosecant squared y dy dx minus x secant squared xy dy dx. We can then factor dy dx out of both these terms. So I've got y times secant squared xy minus 1 equals dy dx times negative cosecant squared y minus x secant squared xy, and then we'll divide both sides by this. So we have y secant squared xy minus 1 all over negative cosecant squared y minus x secant squared of xy is equal to dy dx. Now, we could have done things slightly differently. We could have moved our dy dx terms to this side. What I would have done is just change the sign of everything in this equation. Okay, so we'll look at one last example. We want to find the equation of a tangent line to a curve y equals cos squared x over sine squared x at an x value of pi over 6. So I'll just rewrite our equation down here. So we've got y equals cos squared x over sine squared x. Now, technically looking at this, it looks like we could probably do our quotient rule, but if look a bit more closely, we can actually simplify this first because we know cos over sine is cotangent. So this is the same as y is equal to cotangent squared of x. Now, we're going to need to know our y location when x is pi over 6, so we might as well do that now. So y of pi over 6, or gee, a nicer way to do this is if we have y and we want to solve for when it's pi over 6, that would be cotangent squared of pi over 6. Now, cotangent of pi over 6 is root 3. We're squaring that, so that becomes 3. So we know that we have a coordinate that is pi over 6, comma 3. What we'll do now is take our derivative. So we've got y prime is our derivative of cotangent squared. So we've got 2 cotangent x times d dx of cotangent x. So that would be 2 cotangent x times negative cosecant squared x. Now we want to know it at pi over 6. So that gives us 2 times cotangent of pi over 6 times negative times cosecant squared of pi over 6. So that would be 2 times the square root of 3, which is what cotangent pi over 6 is, times, we've got the negative here, so negative times cosecant squared. So cosecant squared at pi over 6 is 2. So times 2 squared. Now what we end up with is negative 8 root 3. Now we're putting into our slope point form, so y minus y1 equals m times x minus x1. So our equation would be y minus 3 equals negative 8 root 3 times x minus pi over 6.